All right, thank you. All right, so I wanted to talk about something called an RC circuit, RC, and the symbols for a resistor and a symbol for a capacitor. And we can have a voltage source. And what I was trying to say yesterday is that just like if I had two resistors and I wanted to make an equivalent circuit to find the total current, these circuits are in series, and I just make one R1 plus R2. Well, now capacitors are a little bit of a different beast, where for resistance, we have V equals the current times the resistance, but the current voltage relationship for capacitors is the current through a capacitor is the capacitance value, the value you read off of the capacitor, times the derivative of voltage with respect to time. All right, so if we have the resistor and we have the current flowing in that direction, we have VR plus or minus, and then we have these guys right here. In terms of capacitance, right, we still have the current in that direction. We still have VC in that same direction, but rather than this instantaneous equation, meaning there's no time, there's no delay. If I change the current, the voltage would immediately change. If I change the voltage, then the current would immediately change. Here, no, we have a derivative. All right, and so rather than having a voltage times a current times a resistance, you would have this, right? Now that we can get into differential equations, but as I said before, if we look at impedance, right, here's our capacitance value, and then here's something called S, and it's J, which in electrical engineering is an imaginary number, which normally is I, but EEs tend to reserve for current. And then omega, right, omega is 2 pi times the frequency, all right? So by just this one simple substitution, we've gone for something in the time domain, because there's the T, to something in the frequency domain. There's the omega, which is 2 pi f, right? And frequency, 1 hertz, something happens once per second, right? 10 hertz, it happens 10 times per second, right? And then omega is in radians per second. All right. So now I've transformed this into the frequency domain, all right, which we could call omega or we could call f, right? So it could be 2 pi fjc or omega jc. And that allows us to use this kind of functionality, where if I have a resistance and my capacitance, right, and that's ZC and that's ZR, right, I can transform this circuit into a combined impedance, all right? And now what I have is a complex number because this would be real and this would be purely imaginary, all right? So a lot of times in electrical engineering, we kind of bypass the calculus and go straight to the frequency domain, all right? And that means we can do all the same algebra that we did that you learned with resistor manipulation. Same thing for like combining resistors in parallel, all right? Oh, that's a great question. I'll repeat the question. So the impedance is going to be minus J some number omega. And the physical reason why the impedance of a capacitor and the impedance of an inductor are purely imaginary, and this is for ideal, is that these are energy storage elements. They store energy, right? Resistors dissipate energy, right? So if I flow current into a resistor and I have a voltage, you probably remember volt power equals VI, right? Which is giving me a positive number. That means I'm dissipating heat. Heat is coming out of there, right? And so that's a real thing. But if I were to pass current through a capacitor, right, and I have VC and I have IC, power is still the same, but it's going to be imaginary. And so it really just, when the power is imaginary, the energy doesn't go anywhere. It's just stored and transferred and put some, you could say, for later, right? Now, the other, you could say more mathematical part of this is that I have to talk about something called the Laplace Transform, all right? So remember I said S equals J omega, right? Well, actually, that's more than what I can do today, all right? Because I have to show you truthfully, the reason we could derive it mathematically, but the real reason is that capacitors store energy in terms of charge separated by a plate, and inductors store energy by charge moving back and forth. And because it doesn't dissipate, it's really just storing the energy. That's why it's imaginary. Is that good enough, Luca? Okay, thanks. Because, yeah, sometimes I can go off the deep end when I'm answering a question. Any other questions? All right. So let's go back to our circuit here. Now, yesterday we talked about mesh analysis, where if I had a loop here, I could sum the voltages around that loop, and it should equal 0. Oops. Right, and that VR1, according to Ohm's law, is the current times R1. So if I substitute this for that, and then VR2, I just use R2, right? I can write that equation, and I can solve for the current, right? Which is really, right, creating an equivalent circuit where you sum these two resistors, right, and using Ohm's law, right? Well, then what is V, and in this case, I'm interested in VR2. Well, now I know the current. This is a relationship for VR2, and so I have V in R1 plus R2 times R2. And that's the voltage division equation. So while that can take some doing when you're first familiarizing yourself with it, with resistances, you might ask, how do I do that when the current through the capacitor is a differential equation? And you can, right? But we find it easier to switch to impedance, all right? So let's have a capacitor. Now, here was our final thing. And this is voltage division. And whenever I use it, I don't go through all of this. I just know that the voltage from node 2 to ground, or VR2, is really whatever the voltage is across the whole series connection times the resistance in question divided by the sum. Right? It's just something that at some point it's just memorized. It's used so much. But now instead of R1 and R2, right, and I'm going to call that node 2, 2 to 1, which is actually equal to VC. Right? I'm going to have V in, that's the same, except now the assumption is it's a sine wave with a certain frequency. Okay? That's the assumption. With resistances, it can be DC or AC, but in order for this to work at DC, capacitances go to infinity, the impedance. So then I have ZC, then I have ZR plus ZC, right? I substitute the value for impedance wherever I see the impedance for the capacitance. Now, well, that's true. We do like to do some manipulation to get it into like a what we would call a standard format. So we multiply through, right? And then we pull out this, all right? And now what we have is, rather than just this fixed value of V out to V in, it actually changes with frequency, all right? And yeah, at that point you have to have some complex math. But what we can see is that if the frequency were 0, right, then you'd have RC plus 1 divided by RC, which becomes 1, and so then VC becomes V out, V in. Yeah, VC becomes V in, all right? And then if you have a high frequency, this number is trending towards infinity, and so the output voltage, or VC, goes to 0. And if I take the magnitude of that and plot that for frequency, I'm going to get a shape that looks like that, all right? And, well, frequencies, all right, this is called a low pass filter, right? And so these are, low frequencies, and that's kind of right where V out equals V in. So it's passed, right? It could, and so, if I'm talking in a low voice, right, those frequencies would be passed. But then at high frequencies, right, I could be talking in a high voice, but it's attenuated. And so you would hear me talking in that hard voice, but it would be like a whisper, all right? Now, this was all algebra, right? Because complex math is considered algebraic. We actually get to this because of something called the Laplace Transform. And all you have to know is that you can take a ddt. If I take the Laplace transform of that, it turns it into an S. And if I take the Laplace transform of an integral, it turns it into 1 over S. So you're taking something that changes in time, the time domain, right? Like a sine wave, right? And I'm converting it into a frequency relationship. And here I'm taking something, I'm integrating over time, and it's another frequency relationship. And there's essentially something called the table that you look up the inverse. And so I can take this relationship here, right, and bring it back in time and get something called this exponential to k, all right? And so what makes that great is that as long as everything is linear, you can use the Laplace transform, do all your circuit analysis in the S domain, and then when you want to see what it will look like in the time domain, right, you just use a table, right? So what I say is, here, this equation represented in the frequency domain, right? But that equation in the time domain is this. And you just go back and forth. And that's a lot right there, let me tell you. All right, that's a lot to be able to truly get that and manipulate it, that's a lot of work. But what's interesting is that this circuit, right, this RC, can actually be a model for a damper mass system, right, where I'm pushing this. And you can add an inductor as well, and that's a spring, right? It can manipulate that. But also RC networks can be used to model heat transfer. All right. Now, there is like a special case that people, it makes it easier to test the system, and it's called a step. All right. So in time, right, I'm going along, and at some point I go up to 1. All right. Now, and so the way this would work is that I would convert everything to Laplace. This relationship becomes this, R stays R, and this is 1 over SC, right? Then you can take, you manipulate that on Laplace transform, and then you basically get an equation when you come back to the time domain, that output kind of becomes like that. All right. But which you can just, that's a lot of what us, EE98 will go into that in more detail. But I think to show you why we use the Laplace transform, I'll show you the, let's say, the differential equation method. All right. Is that, let's say I have this capacitance and it's charged up, right? And I say, all right, that's IR, and this is IC. Right now, this is something called nodal analysis, where the sum of the currents coming into a node equal the sum of the currents coming out of the node. And so IR is coming out of the node, right? IC is coming out of the node, so that's still on the same side. And they sum to 0, and that's Kirchhoff's current laws, right? And we'll give this a name. We'll just call it V1. So IR1 is just V1 divided by R. And this current is C dV1 dt equals 0. Now I'm going to just move over here where you get V1 equals minus, oh, V1 RC equals minus. Okay. So now you've solved for this, and so essentially what you have is the function. V1 is a function in time, right? We just leave out the time, equal to the negative of its own derivative. And this might be a bit sarcastic, but differential equations, right, uses you set up an equation with calculus, right? Differentials, equations, and integrals, right? And then you come up with some function of time that's dependent on its own derivative. And basically, you keep guessing at things that will make this work out, right? Now, yeah, your differential professors aren't going to say it like that. So the thing would be is V1 like a sine omega t? And you say, well, all right, so if V1 is sine omega t, and I take the derivative of that, right, it's going to be cosine. So then, no, I would need something that I take the derivative, and when it's going to be inverted, but I'll still have the original thing. So sine isn't going to work, right? Well, what if it's x? Well, the derivative of x is 1. X and 1, no matter how you scale them, aren't going to make this equation true. And probably by now you're thinking, yep, there's only one thing that does that. Is that's the derivative of an exponential, right? And so if I take the derivative of this, right, I get 1 over RC e to the minus the original thing, and then I have that minus sign. And so this decaying exponential is the only function that will make that true. All right. Now, a lot of times I've seen this examples in every differential equations textbook, and they use all these techniques. The techniques are essentially maybe more efficient methods of guessing as to what function is going to make that work or not. All right. So you might think, well, wait a second, that was one step. I mean, he drew this circuit, that's one step. One equation, two equation, three equation. And yeah, he kind of knew the answer, so I'll call it 5. And that was a lot faster maybe than explaining this whole impedance method. The thing is this differential equations method for the circuits really only easily works for this example and oops. Essentially, I can have, this circuit, and these can be in any order. And I can have this circuit, and they can be in any order. And it works for these two circuits, which are quite useful. But anything beyond that, and it gets impossible to deal with, and you have to use the impedance method. All right. So that's really quite a bit of information to go over. Are there any questions so far? Okay, so we'll make this recording available. So if there are, I can't see what's going on. So we'll make that recording available. And that's really just kind of a teaser for the classes that if you haven't had them, it'd be a review. I mean, if you haven't had that material, it's just like a teaser of why it's all important. If you had it, it's a good review. And we'll do, oh, here's a chat. So Luca, when you say the first circuit on LT Spice from the which one? Oh, figure 121. All right.
Yeah, I was trying to look at the voltage drops, and when I run the simulation, it doesn't make sense to me because I figured that
This one here.
yeah, because the last circuit, well, right when it gets to 2, for example, at point 2, it should be the biggest voltage drop, right? Or either point 2 or point 3.
It, listen, I'm really sorry, but they double booked me at this point, and I'm gonna have to scoot. But yeah, um, I got to scoot. All right.
Okay, that's
Can
fine.
you email me that question?
Yeah.
Yeah, I'm really sorry. I thought I didn't have to go somewhere, and now I'm getting texted that I have to. All right, I gotta go. Sorry. Elisa, you can when